All right, hello everyone. So today's short video, we are going to focus on alkenes, because those are the type of molecules we're going to be using for the next quite a few class periods to talk about reactions. So remember, alkenes, right, that's with an E, all have a C double bond C, right? And there are 4 additional positions for groups to be bonded. These 2 carbons are both sp3 for their hybridization, and this is trigonal planar, right? So those 2 things are both flat. Now we've seen alkenes quite a few times before, and in fact we've seen a number of alkenes. This is sort of where the semester began in many ways, with drawing isomers. So there are some examples of C4H8 isomers. And this one would have been 1-butene, right? That should be familiar. This one was 2-butene, and this one was also 2-butene. But the difference between these 2 is the position of the H's. So here and here, and there and there. So this one where the H's are on opposite, we've called trans. And this one where they're pointed the same way, we've called cis. And remember, trans and cis are diastereomers. Those are stereoisomers. This 1-butene with respect to those is just a constitutional or structural isomer. So that goes back to chapter 1, where the double bond is in a different position. Now, for simple molecules, trans and cis work very well. But as it turns out, if you get larger, more complex molecules, very often there are not 2 H's or 2 identical groups to look at. So there is a different way to name diastereomer alkenes, and that is the so-called E and Z naming. Okay, so E and Z, the IUPAC, we're going to assign priority to groups, sort of like we did for chirality centers. So it's in that same vein. It works a little differently, but we'll see how this goes. So what we need to do is essentially divide our alkene in half at the double bond. And we're going to look at each half separately. So here, this is a hydrogen, and that is a carbon with its H's. This is an H, that's a carbon. And then same thing down here. So we're going to look at the 2 atoms directly bonded to the alkene. Carbon is atomic number 6, H is atomic number 1. So this is going to get our A, this is going to get our B. Maybe I should do those in red just to emphasize that we're assigning priority. So that's A, that's B. Same thing on the other side. Carbon is number 6, that's A, hydrogen B. So if the A groups are on the same side, okay, so Z is A groups the same side. E is A groups opposite. So the IUPAC, the technical correct name for this one would be Z2-butene. And up here, again, carbon is A, hydrogen's B. Here, carbon is A, hydrogen is B. So this one would be E2-butene. Okay, so for these simple molecules, cis and trans works fine, but for very many others, it does not at all. And I at least want to give you one example of that, and then there'll be many more of those on the worksheets. And this is even going to be a relatively simple molecule. So how about something like, maybe I'll do one more carbon there, something like this. So this is 1, 2, 3, 4, 5. So that is a 2-pentene. And we have a 2-chlorine. Well, what about our groups? Well, we have chlorine. We have this carbon. We have this H, and we have this carbon with its H's. Well, there are no 2 identical groups there. So cis and trans doesn't apply. But we can definitely do this. Chlorine is by far the highest atomic number. So again, if we divide our alkene, this is going to be A on this end, this is B. Over here, this one's A, this one's B. So our A groups are on the same side. So this is going to be Z 2-chloro-2-pentene. And again, given those four groups, we could not easily, or at all really, label that cis or trans because there are not two identical groups. There are not two H's or two methyls or two of anything. Okay, so E and Z applies to all alkenes. And remember again, like the one butene we looked at, the two groups on the end are identical. So there's no cis, trans, no EZ, nothing like that. But as long as the alkene is in the middle of the molecule somewhere, you are generally going to have E and Z. Now, there are of course exceptions to everything. Don't also forget that we can have cyclic alkenes. So we could have something like this, or something like this. So this 4-carbon one would be cyclobutene, and this one is cyclohexene. And notice in these cases, the H's are pointing the same direction. So technically, I suppose you could call these Z, cyclobutene and cyclohexene, but realistically, there is no possible way for those to be in any other position because these two are tied together. So the E and Z we usually do not use. No, and we didn't use cis and trans for cyclic alkenes either back when we talked about them several chapters ago. Okay, so that's just a couple of simple examples of cyclo or cyclic alkenes. Now the other big thing we need to talk about with respect to alkenes is their stability or their energy. Okay, so alkene stability. Because it turns out not all alkenes have the same energy or have the same stability. And I will go back to our original molecules that I had drawn up here a little while ago. Here is 1-butene, this is E2-butene and Z2-butene. Those are all isomers of each other, and in fact these two are stereoisomers of each other. So you'd say, oh, well of course those have to have the same energy, but they absolutely do not. And if you remember back to General Chem when you did the calorimetry, remember that? You measured the heat associated with a reaction? Well, you can do the same thing for these kinds of organic molecules. So if we did a reaction with each of these three molecules and measured the heat associated with it, we would see that this one would be the most exothermic, depending on what the reaction was, if it's hydrogenation adding H especially. So this would release the most energy, this one would release the least amount of energy, and this one would be in the middle. And that's because these molecules have different stabilities to begin with. So if you did hundreds and hundreds and hundreds of reactions like this, and these have all been done, we're not going to do them, you come up with the following, okay? That tetra-substituted is the most stable. So this is going to be, and I suppose I should erase my alkenes here because that one is most definitely not tetra-substituted. I'll give you some examples. And then we have tri-substituted, then di-substituted, and then finally mono-substituted. So what do these things look like? Well, tetra means 4. So in this case, when you have your alkene, all 4 of these, I guess I'll just use a carbon, are additional carbon groups. Okay, and that could be just a CH3, or it could be a long chain, it could be anything. Tri-substituted, well, 3 of them, not shockingly, right? 3 of these are going to be carbons and an H. Di-substituted, that's some of the ones I already had. So for those, there are actually 3 of them. That would be the E, we already saw that. So this is Z, this is E, and then there's one more possibility yet where both of the C's are on the same end. And they go in this order. right? So this di-substituted goes next, then the E, then the Z, and then finally mono-substituted is simply one carbon group and 3 H's. And you might be thinking, okay, that's great, but why do we care? Well, it turns out when we go to make alkenes, the stability of them is extremely important. And in just the next day or two, we're going to start to see reactions of alkenes, that is using alkenes to do other things with them. It turns out that which alkene you start with is critically important there too for the type of product you get. So this stability, again, tetra-substituted most stable, and then I guess I should say mono-substituted over here, this is the least. Okay, and then tri-substituted, then the 3 different di-substituteds, those are not the same as each other, they go in that order, and then finally mono-substituted here is the least stable. Okay, so with that, that's another introduction to alkenes, and we'll start to see alkene reactions next week then in class.